In this today topics, we will discuss about bearings. Now, first we will see what is bearing. A bearing is a machine member which supports, guides, and reduces the friction of motion between the fixed and the moving machine part. So, this is the main function of the bearing. That is nothing but it supports the another component, it guides the component, and it reduces the friction between the fixed component and the moving component. So that is the first function of the bearing, and the supporting device is called as bearing. So always the bearing is a supporting device, and it is a stationary element which carries a load. So always the bearing is a stationary element, it is not a movable element. The portion of the shaft supported the general. Now you can see whatever the figure you are seeing, the first figure, it is the one of the example of ball bearings. And sure. So here, and the second figure, so it is also a example of ball bearing. So here the bearing is here the shaft is supported by the bearing. So therefore you can see a bearing is a machine member which supports, always the bearing is, always the shaft is supported by the bearings. And sure, and it reduces the friction between the fixed component and the movable component. And sure, the supporting device is always, we'll call it as a bearing. Now in the second figure you can see the whatever the thing you can see in the red color, it is nothing but the bearing, and this is nothing but shaft. Here the shaft is supported by the bearing. So whatever the load acting is not directly acts on the shaft, it is acts on the bearing, then it is transferred to the shaft. So we can able to reduce the direct load acting on the shaft with the help of the bearing. And sure, and the portion of the shaft supported is called as general. So here you can see in the total bearing, so whatever the portion it is supported by the bearing, see this is the portion, that portion we will call it as a journal. And sure, which portion the shaft is supported, that portion we will call it as a journal. So this is the main function of the bearing. And sure, always bearings are used as a supporting devices. It is used to support the shaft or the rotating object. And sure, next we will see what are the different types of bearings and their uses. So first type of bearing is nothing but ball bearing. So whatever the figure you can see, it is nothing but ball bearing. This type of bearings you have seen in the bicycles. So inside the shaft is supported, the shaft is placed, and the shaft is rotating object, and the bearing is the stationary object. Whatever the portion you are seeing, this portion we will call it as a journal. And sure, so this type of ball bearings are used for high speed or high precision applications, and it is a large range of standard forms. It is having different standards, and this type of ball bearings are used to carry radial and axial loads. So whenever the radial and the axial loads is acting, then we are going to use the ball bearing. So this is the figure. It is the example of the ball bearings. Sure. Next is the roller bearings. Sure. So whatever the figures you are seeing, these are the examples of the roller bearing. So it is of three types. It may be cylindrical rollers. So it is the bearings in the form of cylindrical shape, and tapered roller bearing. So whatever the thing you are seeing here, it is a tapered. So that is nothing but the length is continuously that is the diameter is continuously decreasing from one end to the another end. So we will call it as tapered roller bearing. So here the bearing is in the form of tapered shape, and spherical roller bearing. So here the bearing is in the form of spherical shape. So that way we will call it as spherical roller bearing. And sure. So this type of roller bearings are used for high load capacity. So if you want to, if you want to carry a higher load, then we are going to use the ball bearings. And sure, and can withstand high axial load compared to the ball bearings. So the main advantage of this roller bearings, it can able to withstand higher loads, and it can able to withstand high axial loads. Next is mounted bearing. So whatever the figures you are seeing, this is nothing but mounted bearings. And so it is mounted on the some of the components with the help of the bolt or nuts or something. So we'll see here housed unit reduce mounted corner protection issues. So with the help of this mounting component, we can able to protect the bearings, and shaft usually held in the place with set screw. So and the shaft is held inside this bearing, and the shaft is fixed with the help of the screws. You can see the gaps here. So we are going to place the set screw, and we are going to fix the shaft. Allow adjustment of the supporting component, so we can able to support the component. And this type of mounted bearings are you mainly used for low and medium speed application. We can't use this mounted bearing for high speed applications. Only we can use this mounted bearing for medium and low speed applications. Next type of bearing is linear bearing. So whatever the figure you are seeing, it is a type of linear bearings. So it is having lower friction and higher accuracy compared to the bushes. And sure, so linear bearings having less friction and having higher accuracy, and it is more costly and complex compared to the bushing. So here you can see whatever things you are seeing, this one, this is nothing but the bearings. Inside this we are going to place a rotating component, and this is the stationary component. And next type of bearing is jewel bearing. So what are the things you are using? This is a jewel bearings. What are the things you are seeing in the pink color? This is nothing but bearings. So this type of bearings is used in watches, and that is, and also this type of bearings are used for small load carrying capacities. And sure. So that when they told that loads are small and this supported rotating shafts are thinning, and should it use it for medium loads and small loads. Sure. So whatever the thing you are seeing, it is one of the applications where we can use this jewel bearing instead. This type of bearings are used in small watches, and you can see the bearings there where and all they are used. Sure. So this is the another type of bearing that is nothing but jewel bearing. So these are the different types of bearings. One is the ball bearing, roller bearing, mounted bearings, linear bearing, and the jewel bearing. Here there are, depending upon the load, we are going to use the bearings. And sure. So this is bearing and the different types of bearing. The bearing is mostly used for supports the rotating object. That is the main function of the bearings. And sure. Next we will see bearing characteristic number and bearing modulus for journal bearing. And sure. Now the coefficient of friction, that is nothing but mu, it depends upon three-dimensional parameters, that is neta n dash by p, d by c, and l by d. Whatever the coefficient of friction mu, it depends upon these three factors. One is neta n dash by p, and another term is d by c, and another term is l by d, where neta is nothing but absolute viscosity. Always it is represented by pascals. N dash is nothing but speed in RPS, not in RPM, it is in RPS, revolutions per second. P is nothing but bearing pressure on projected area, and this P can be calculated by using the formula W divided by L into D, where W is nothing but load, L is nothing but length of the bearing, D is nothing but diameter of the journal, where D is nothing but small d, diameter of the journal. C is nothing but diametrical clearance. In the last session, I told what is C, and L is nothing but length of the bearing. L is nothing but length of the bearing. So therefore, the parameter neta n dash by p is called as bearing characteristic number, and it is a dimensionless number. So whatever the dimensionless number we are having, that is neta n dash by p, this is nothing but bearing characteristic number, and it is a dimensionless number. Sure. So now we can see in the next graph, here there is in this graph we are having x-axis is bearing characteristic number and y-axis is coefficient of friction. Already I told that the coefficient of friction is depends upon the dimensionless number, that is bearing characteristic number neta n dash by p. Now here there is three things. One is thin film, semi-fluid, and the thick film. In this figure, the curve from P to Q is nothing but thick film lubrication, and the curve from Q to R is nothing but semi-fluid, and from R to S is nothing but thin film. Here, when it comes to Q to R, the neta, that is nothing but viscosity of the fluid, and the speed will be reduces, but the pressure will be increases. Once pressure will be increases, there is a uh, there is a contact between journal and the there is a contact between the bearing and the shaft. Therefore, thin film lubrication will generated from R to S. So thin film lubrication will take place when the viscosity and the speed is less, but the pressure is more. Then metal to metal contact takes place from R to S. Therefore, there is a thin film lubrication. If there is a lubricant, instead of already there is a lubricant, but at the same time there is a contact between the shaft and the bearing takes place due to the increase in the pressure. Since pressure is at the denominator, due to this increase in pressure, there is a metal to metal contact takes place between the R and the S. And sure. So always here neta n dash by p is nothing but bearing characteristic number. Understood? Next we will see what is Summerfield number. So Summerfield number, it is denoted by S. So it is also another dimensionless parameter. So it is also another dimensionless parameter used in the lubrication analysis based on hydrodynamic theory. Already in the last session we have discussed what is hydrodynamic lubrication. It can be shown that the Summerfield number is a function of altitude only. It may be plotted against the quantity mu d by c, where mu is nothing but coefficient of friction, d is nothing but diameter of the journal, c is nothing but diametrical clearance. So, which is also a function of altitude only, and the coefficient of journal friction can be obtained. Therefore, the Summerfield number is represented by neta n dash by p into d by c whole square, or neta n dash by p d by c can be written as 1 divided by xi, where xi is equal to c divided by d, diametrical clearance ratio. This is nothing but diametrical clearance ratio, c by d. Therefore, we can write it as 1 divided by xi square. So here you can see in the figure, so it can be plotted as that is the mu d by c versus the Summerfield number. As the Summerfield number increases, the coefficient of that is the term mu d by c is also increases. So this is the formula we are going to use to calculate the Summerfield number by using the graph, that is Summerfield number versus mu d by c. So next we will see the derivation, that is nothing but Petrov's equation. So it is a derivation. So by using this Petrov, he has given some formula to calculate the coefficient of friction mu between the journal and the bearing. And now here, whatever the figure you are seeing, so this is the journal and this is the bearing. This is the journal and this is the bearing. So consider a vertical shaft rotating in the guide bearing. So the whatever the journal, it is nothing but bearing. So always the diameter of the journal is equal to the diameter of the bearing. So this shaft is rotating inside the bearing. So we are going to assume some assumptions, that is always it carries a very small load. So whatever the type of bearing you are using, we are considered here, it carries a very small load. The clearance C is completely filled with oil. So whatever the clearance you are seeing, this is nothing but it is completely filled with the oil. The end leakage is completely negligible. There is no leakage inside the bearing. The oil used is of high viscosity. Whatever the oil you are using, it is having high viscosity. The journal revolves at very high speed, that is the shaft is rotating at very high speed. The bearing run concentrically. So these are some of the assumptions we are going to consider in the derivation of mu based on the Petrov's equation. Now here where small d is nothing but diameter of the journal, or we can call it as C, that is nothing but this is nothing but journal or the shaft. C is nothing but diametrical clearance. N dash is nothing but speed of the shaft or journal in RPS. N dash is equal to N divided by 60. L is the length of the bearing. Psi is nothing but diametrical clearance ratio, C by D. Neta is nothing but viscosity of oil in Pascal. These are the notations. Now we are going to derive. First, we are considered the shearing stress. And sure, shearing stress tau is equal to neta into V divided by H, where neta is nothing but viscosity of the oil, V is nothing but velocity, and H is nothing but the distance, that is nothing but C divided by 2. So therefore, neta into velocity can be written as here pi d n dash, where n dash is nothing but n divided by 60. So we are writing pi d n divided by 60 in the form of pi d n dash. So we are writing velocity in the form of pi d n dash divided by h is nothing but c divided by 2. Total clearance is nothing but 2. Half of that one is c divided by 2, that is nothing but h. If you simplify, so we will get, if you simplify, you will get 2 pi d neta n dash divided by c. So this is nothing but shear stress acting on the bearings. Now we are considered this surface area, where area is equal to pi into d into L. So we are considered only the surface area. Therefore, force is equal to, always we know the formula, shear stress is equal to force divided by area. Therefore, force is equal to shear stress into area. Substitute shear stress, what you will get, into area. If you simplify here, we will get 2 pi into pi, pi square, d into d, d square, n dash neta L divided by C. That is nothing but force we got. Next, torque. So always we know that torque is equal to force into radius. Why we are considering a radius, since it is a circular object, always torque is equal to force into radius, where force into radius is equal to d divided by 2. Force is equal to, just now you have calculated in the previous step, you have calculated, we got force is equal to here 2 pi square d square and n dash neta L divided by 2. Substitute here into d divided by 2. So here these two get cancel. So again we can write C is equal to, or we can write again, if you simplify, we will get pi square d square capacities n dash neta L divided by C divided by 2. I brought this d divided below the numerator, then we will get C divided by 2. And we can write it as C divided by 2 is nothing but xi, where xi is nothing but, we can write it as xi is equal to C divided by d, that is nothing but diametrical clearance ratio. Now this is nothing but torque mt, but we know that torque is equal to mu w into d divided by 2, where mu into w is nothing but frictional force, w is nothing but p into a, load into area. That can be written as p, load can be written as L into d, p is equal to bearing pressure. And sure, so this is another formula to calculate torque mt. Now simplify these two equations. Now we are having mt here. Simplify these two equations. This is equation number 1 and this is equation number 2. So writing equation 1 and 2. Now if you simplify, finally we will get pi is equal to, that is mu coefficient of friction, mu is equal to, cross multiply this one, 2 pi square, and sure, neta n dash divided by p into 1 divided by xi. Here d square get cancelled. Finally we will get mu is equal to 2 pi square neta n dash by P into 1 divided by Xi. So this is the formula to calculate the coefficient of friction based upon the Petrov's equation. And so here first we have considered the force, that is shear stress. Then we are considered the force. Force is equal to shear stress into area. So we have calculated the formula for force. Then we have considered the torque. Torque is equal to force into radius. Then we have calculated the formula for torque. And we have equated equation 1 and equation 2. Then finally we are getting the formula for mu. So this we are going to use to calculate mu based upon the Petrov's equation. And next is another formula, that is to calculate coefficient of friction by Mekis. So it is another scientist who have given another formula to calculate the coefficient of friction. So this is the formula. We don't have any derivation. So directly we are taking the formula. So mu is equal to Ka neta n dash by P into 1 by Z 10 into 10 to the power of minus 10 plus delta mu. This is the formula we are going to use to calculate mu based upon the Mekis. And so here Ka is nothing but 1.95 into 10 to the power of 11 for full journal bearing, or 5.4 into 10 to the power of 8 beta for partial bearing. Beta is nothing but altitude angle. Neta is absolute viscosity. Delta mu is nothing but factor to correct for any leakage. If there is any leakage, we are going to consider this delta mu. Xi is nothing but diametrical clearance ratio, and n dash is nothing but speed, and P is nothing but bearing pressure. So this is the formula to calculate mu based upon the Mekis equation. Sure. So this completes the theory related to the lubrication and bearing. So in this today's session, we have discussed about what is bearing, what are the different types of bearing, and what is bearing characteristic number neta n dash by P, what is Summerfield number, Petrov's derivation, and Mekis formula.